Do you know the star Mizar in the constellation of Ursa Major is actually consisted of 4 stars? If you know that, that's cool, because today we are not going to talk about this star. But what is interesting, though, is that the main star of the Mizar system is an A-type main sequence star, and that is important. How life feels around an A-type star? Can this kind of stars produce habitable worlds? If our sun were replaced by a much hotter, brighter A-type star, what would life look like? Could planets around these stars actually be habitable? Before answering that question, let's first understand what an A-type star actually is. Astronomers classify stars by temperature. The familiar sequence is O, B, A, F, G, K and M, running from the hottest stars to the coolest. Our own sun is a G-type star, with a surface temperature of about 5,800 Kelvin. Move one step hotter, and you reach F-type stars. A good example is Procyon A, shining at roughly 6,500 Kelvin. Another step upward brings us to A-type stars. The brightest star in Earth's night sky, Sirius A, belongs to this category, with a surface temperature close to 10,000 Kelvin. That temperature difference may not sound dramatic, but the physics changes enormously. Hotter stars radiate much more energy. Although Sirius A is only about twice as massive as the Sun, it shines roughly 25 times brighter. Its habitable zone therefore lies much farther away, around 5 astronomical units from the star, roughly the distance of Jupiter's orbit in our own solar system. From a distance, an Earth-like planet orbiting Sirius A might actually look quite inviting. The star is brilliant. The habitable zone is wide. There is plenty of energy available. So, where is the catch? Well, prepare for that, because there are a bunch of catches that would squeeze the habitable planets apart. The first problem is time. Life does not simply appear because a planet happens to sit inside the habitable zone. A rocky planet has to finish forming, its surface must cool, oceans have to condense, an atmosphere has to stabilize, and carbon dioxide, which is very common inside a star system, must be gradually removed through weathering. Plate tectonics and the carbon silicate cycle need hundreds of millions of years to begin regulating climate. Only after all of that can biology slowly reshape the atmosphere. On Earth, this process took almost 1.5 billion years. What's more, on Earth we know that single-celled organisms appeared relatively early, but complex multicellular life required more than 3 billion years to evolve. This is where stellar lifetime becomes critical. The Sun will remain on the main sequence for about 5 more billion years. The total life length is about 10 billion years. But if you scale the size of the star up, that star has more to fuse, but the speed of fusion is exponentially faster, so its life gets shorter. Late F-type stars also survive for several billion years, providing enough time for an Earth-like climate system to develop. But once we move toward early F-type stars and especially A-type stars, the clock starts running much faster. An A-type star typically remains on the main sequence for only around 1 to 2 billion years. Sirius A has already lived comfortably for more than 300 million years, but do you know its little companion, Sirius B? That's the bigger sibling. It was a B-type star, about 5 times the mass of our Sun, and ran out of its fuel in just less than 200 million years, so when humans emerge, they see a tiny white dwarf. The same story goes for Sirius A, except it will be way longer, about less than a billion years. Good luck if Sirius A has a planet. Even it is inside the habitable zone initially, the star itself goes brighter and brighter during the main sequence period and it is changing way faster than smaller stars like our Sun, and the planet would be too hot long before the star dies. So before asking whether life can evolve, we first have to ask whether the planet even has enough time to become Earth-like in the first place. Now, suppose, however, that somehow time is not the limiting factor. Perhaps the star is a relatively low-mass and metal-rich A-type star with a lifetime more than 2 billion years. If you don't know how metal-rich works, basically it makes the star less opaque and less luminous, generally leads to a longer main sequence lifetime. Or perhaps life evolves unusually quickly, while the Earth was just not lucky enough? With all that, would the environment actually resemble Earth? Sadly, still probably not. The biggest difference comes from the star's spectrum. F-type and A-type stars are hotter and bluer than the Sun. A much larger fraction of their radiation is emitted as ultraviolet light. Ultraviolet radiation is energetic enough to damage DNA, alter atmospheric chemistry, and drive photochemical reactions that barely occur under sunlight on Earth. Climate models suggest that an Earth-like atmosphere placed inside the habitable zone of an F-type star could receive between roughly 2.5 and 7 times as much ultraviolet radiation as Earth does today. To keep surface conditions similar to ours, such a planet would probably need a substantially thicker ozone layer, as a thicker ozone layer absorbs more ultraviolet radiation. That, in turn, heats the stratosphere more efficiently, strengthening the temperature inversion above the troposphere. As a result, the vertical temperature structure of the atmosphere could differ significantly from Earth's, affecting cloud formation, atmospheric circulation, and even weather patterns. Fortunately, ultraviolet radiation is not necessarily a fatal problem. Because A-type stars are more luminous, their habitable zones are also much wider, roughly 3 to 6 times wider than the Sun's, with thick atmosphere up to 9 astronomical units. Near the outer edge of that habitable zone, ultraviolet flux may fall to levels comparable to, or even lower than, those on Earth. So ultraviolet radiation is not a universal disadvantage, it depends strongly on orbital distance. But the blue spectrum introduces another, much subtler problem. Ice. On Earth, snow and ice already reflect sunlight efficiently. However, they reflect visible light and ultraviolet light much more effectively than near-infrared radiation. Since F-type and A-type stars emit a larger fraction of their energy at exactly those wavelengths, frozen surfaces become even brighter. That strengthens one of the most important positive feedback loops in planetary climate. More ice reflects more sunlight, lower temperatures create even more ice, which reflects even more sunlight. Eventually the entire planet can freeze over. Climate simulations show just how sensitive this effect can be. Around an F-type star, reducing stellar radiation by only about 2% may be enough to trigger a global snowball Earth. For Earth orbiting the Sun, roughly 8% is required. For a planet around a cool red dwarf, stellar radiation has to fall by nearly 27% before complete global glaciation occurs. In other words, planets orbiting hotter stars may possess wider theoretical habitable zones. But near the outer edge, they can lose climate stability much more easily than Earth. And even if the climate itself behaves perfectly, the architecture of the planetary system introduces yet another complication. More massive stars generally form from more massive protoplanetary disks, which means more raw material, naturally means more planets. And statistically, giant planets become much more common. Around Sun-like stars, only about 3% are known to host Jupiter-like giant planets, but around A-type stars with roughly twice the Sun's mass, that probability rises to around 14%. If an Earth-like planet exists within the habitable zone of an A-type star, there is therefore a much higher chance that one or more giant planets are orbiting nearby. Those giants continually perturb the smaller planet's orbit, as its orbital eccentricity may oscillate more strongly and its axial tilt may vary more dramatically over millions of years. Tropics expand and contract, polar ice advances and retreats, rain belts migrate. So even without considering ultraviolet radiation or ice albedo feedback, these long-term orbital variations alone could make climates around F-type and A-type stars considerably less stable than Earth's. Although, this would probably create a strong environmental forcing that nudges life to evolve much more quickly. Speaking to mass, interestingly, those same massive disks also make another type of planet much more likely. Super-Earths. Instead of stopping at one Earth mass, rocky planets may continue growing until they reach 2, 5, or even 10 times Earth's mass. That changes almost everything. A stronger gravitational field allows these planets to retain thicker atmospheres. Carbon dioxide, nitrogen and water vapor escape much less efficiently. Higher atmospheric pressure increases the greenhouse effect while also storing heat more effectively, reducing day-night and seasonal temperature swings. For planets around these stars, such dense atmospheres may even provide an unexpected advantage, as a thicker atmosphere can absorb ultraviolet radiation more effectively, while supporting a larger ozone column that shields the surface. On the other hand, there is a fine line between protection and catastrophe, as too much greenhouse warming may eventually trigger a runaway greenhouse effect, pushing the planet toward conditions resembling Venus. Also, the planet's interior changes as well. Because super-Earths contain more radioactive material and experience much higher internal pressures, they may remain geologically active for much longer than Earth. Volcanoes would replenish atmospheric gases. Meanwhile, the carbon silicate cycle would keep removing excess carbon dioxide whenever temperatures became too high. This long-term geological thermostat is one of the reasons Earth has remained habitable for billions of years. In principle, a super-Earth could perform that job even better. So larger planets are not necessarily less habitable. In some respects, they might actually outperform Earth. But, eventually, size becomes a disadvantage again. As gravity approaches roughly twice Earth's, mountains become increasingly difficult to support. Continents flatten. Ocean basins deepen. If the planet begins with only slightly more water than Earth, it may evolve into an ocean world. As you may have guessed it, a planet covered by water may provide fewer opportunities for complex life than one with both oceans and continents. So does that mean A-type stars are hopeless for life? Not necessarily. These are just all based on the assumption that current known life form on Earth is the only possible form in the universe, which is probably wrong, just like the way they think about the universe thousands of years ago. So in the end, this is more like an Earth-like discussion, and Earth-like doesn't mean lifelike. If you are in the Mizar system and using Galactic YouTube to watch this video, A-type stars are cool, and please subscribe.